Afternoon. So I have arrived and it looks like we've got a couple contractors working. Looks like potentially an HVAC guy, maybe two HVAC guys. I think they're running some ducts and it looks like they're running your line set there, this piece here. So I'll probably jump on your roof, walk the whole roof and go around the exterior, try to give them as much leeway as possible, and then work my way on the inside. About to jump on your roof, and the first thing I like to do is take a look underneath the shingles to make sure you have underlayment, and you do. It's that white piece on top of this blue sheathing here. That helps to ensure that if any water gets beneath these shingles, that it goes onto the underlayment and then out of the roof. So an additional layer of protection. You have a good weather resistant barrier. I'm always happy to see this kind. This is your weather resistant barrier. I like this kind because it not only sheds water and stops air infiltration, it also helps to mitigate humidity infiltration. These have what's called a perm rating, and so they allow enough vapor to move to and fro, but they also help to slow the process, so it's great for energy efficiency. And this is a non-woven, high-density polyolefin wrap, and always happy to see that. I will be inspecting how they've shingled it. So here's an example where we have one piece, and you might be able to see through. There's a piece right here, which is this lower course. And then this upper course laps over it in the direction of water flow. And then you want to see that it is properly integrated with what's called your step flashing. This is very, very important. So I'll be looking closely at this as well. And then just in general, your roof covering, want to make sure that your shingles aren't racked, or that there's no damage or exposed nails. And that they also have appropriate what's called kick out flashing, and they do, where the flashing comes and literally kicks out, and that's to keep water from diverting behind the wall and causing excessive saturation. So far so good. While I'm up here, I like to make sure that your windows are installed plumb and level, so we can see we're looking pretty good out the gate here. And of course I can't get to all of them, unfortunately. There's a couple over there I wouldn't be able to necessarily get to, though I can get to the one in the middle with a little bit of a reach. It is nice to be able to make sure that they have installed these correctly. And the other thing I like to check for while I'm looking at these is that they have properly flashed these windows. So you'll see, and they've done a good job. They've cut the weather resistant barrier to allow them to flash the top of the window, and then they've shingled that weather resistant barrier back over. They have run these on the sides, and these shingle over these, so all in the flow of the direction of water. And this again helps with air tightness and ensuring that your home stays watertight. Jumped up to the main part of your roof, and I like to make sure that the penetrations through the roof are properly flashed. This part is paramount, and so far these look great. So this is a vent boot, and it seals very tightly around this plumbing ventilation, and they have properly integrated this boot into the shingles, again always in the direction of water flow. So the plumbing penetration flashing looks quite good. As you can see, we do have some penetrations that haven't been utilized yet. I'm not sure what the story is on those. The good news is I always jump back on top of the roof at the final inspection. So just because they're not done today doesn't mean that they wouldn't get inspected. We still have an opportunity for that. So I will keep you posted, particularly on the final as it relates to any of these penetrations. Okay, so I'm looking at your portal frame, and the portal frame is basically just the beam that spans over this garage opening. The portal frame has two functions. It, just like any beam, supports gravitational loads. But its other function, which not as many people know about, is it supports racking loads. So you can imagine this wall is like a wind sail. Well, typically in a wall, you would have a lot of wall section on the other side. But in this case, you have very little wall section. You've got this tiny little, what we call wing wall. And that's just not enough to naturally keep this wall upright. So engineers developed something called a portal frame, which uses this sheathing here. It overlaps the beam. There's a really robust nail pattern. So when this beam wants to rack left and right, it transfers it into the sheathing, into the studs, and down into the foundation. And here we see they even have some really robust hold downs. These are probably HTT4s. Yep, HTT4s. The problem at hand is these anchor bolts here are not placed what's called middle third. So if you could cut this plate into 3 sections, these should be within that middle third section. And we want them within the middle third of the plate because the further you push this off towards the wall, the more likely that you'll have breakout of this material. The anchors aren't acting as concentrically, so they're sort of eccentrically placed. So they're just not going to be able to withstand these racking forces as easily. So I do think that a structural engineer should have the final say on how we rectify that, unless the building plans give an alternative retrofit anchor specification. I haven't come across the building plans, unfortunately, but they do have the layouts and the truss profiles, which will still be immensely helpful. So I'll keep my eye out for those plans, but in the meantime, this will definitely be on another item that I think will benefit from some extra context. This metal thing here that you see, that's called a post cap. And in this case, its main function is to resist uplift forces. And what I mean by that is this beam right here supports these mono trusses. And ultimately what happens is when wind blows over these trusses, you have something called Bernoulli's principle, where when the velocity of something increases, the pressure goes down. So when wind velocity increases, the pressure goes down so much that these actually want to suck off of the beam and the wall here. And we call that uplift. And we restrain it with these guys here, these little metal clips. Those are called hurricane clips, or H2.5As. And the cumulative uplift imposed on this beam, if it's enough, needs to be resolved with a post cap. And I'm calling this out as problematic because this little flange here shouldn't actually be going this direction. It should actually be sandwiching this beam. And we can see it's sandwiching this beam on the other side. We can't see it very easily, perhaps I can zoom in. But that flange goes between these two pieces of lumber and goes up vertically along the beam. And that way, if this picks up, these nails are perpendicular to the load path. These nails here would be parallel to the load path, and that places that fastener in withdrawal. When you place a nail in withdrawal, it has considerably less capacity. Now, this may be okay. It may be okay as is. If the cumulative uplift isn't so great here, they might be able to give this an easy pass. But I still think it should make the report. Another item that I think will benefit from some extra context. This metal thing here that you see, that's called a post cap. And in this case, its main function is to resist uplift forces. And what I mean by that is this beam right here supports these mono trusses. And ultimately what happens is when wind blows over these trusses, you have something called Bernoulli's principle, where when the velocity of something increases, the pressure goes down. So when wind velocity increases, the pressure goes down so much that these actually want to suck off of the beam and the wall here. And we call that uplift. And we restrain it with these guys here, these these little metal clips. Those are called hurricane clips, or H2.5As. And the cumulative uplift imposed on this beam, if it's enough, needs to be resolved with a post cap. And I'm calling this out as problematic because this little flange here shouldn't actually be going this direction. It should actually be sandwiching this beam. And we can see it's sandwiching this beam on the other side. We can't see it very easily, perhaps I can zoom in. But that flange goes between these two pieces of lumber and goes up vertically along the beam. And that way, if this picks up, these nails are perpendicular to the load path. These nails here would be parallel to the load path, and that places that fastener in withdrawal. When you place a nail in withdrawal, it has considerably less capacity. Now, this may be okay. It may be okay as is. If the cumulative uplift isn't so great here, they might be able to give this an easy pass. But I still think it should make the report. So right now I'm looking at your roof trusses, and there's a few things I like to look for. The first thing is I like to check these diagrams to make sure there's no bracing, or if there is bracing, that they've installed it correctly. And in this case, there's no bracing on these trusses. The other thing I like to make sure is that these are installed the correct way. You can either put these, you can flip them the wrong way, or you can flip them upside down. It happens both ways. And I like to make sure that these are installed correctly oriented in both orientations. Once I've got all the information I need from each individual truss, because there's multiple truss profiles, they're all quite a bit different, I will go through and individually check every single one of these metal plates. They're called gusset joints. I want to make sure that they are properly pressed into the truss, and then I also check to make sure there's no damage on the truss, that they're installed plumb, and that at intermediate bearing points like this wall, that the gussets align over that wall. So quite a few things to check with trusses. The same concept will apply upstairs because you have roof trusses. So they're just like this, but an even bigger scale. An interesting item that I think will require some additional context. This is truss, this right here is truss 2F6. And if we look at its truss profile, flatten it out over here, it requires something called uplift. And this is a very rare condition for a typical floor truss. So it wants uplift right here at this joint. The reason why this wants to pick upwards is because this span here is greater than this span here. And when you apply a load to this area of the truss, it will want to use this as a pivot point, essentially, and pick this side up, or as a fulcrum, if you will, and will want to pick this side up. And you need a tension tie here to secure it to the wall. So there are two trusses on that are going to be on your report that are going to require truss uplift. Easy fix, but definitely buried in the notes of this particular truss profile here. So they want an H2.5A Simpson strong tie. All right, so I am looking at your roof trusses. Fortunately, we have some of these profiles on hand. We've got the layouts. And again, after analyzing these profiles, I'm looking at the trusses themselves, and we can see we've got loads of gussets again, but this particular truss is missing a gusset plate right here. And it's on what's called a girder truss, and a girder truss is a truss that supports other trusses. We can actually see this is where those other trusses are, which are right here. Those little guys that are kind of coming in perpendicularly. The joint that we're missing, and this is way beyond a home inspection, but for the sake of just edification, is at joint 17. And if we look in the webs, we've got 1117 and 1017. 1017 since this is a diagonal member, it's likely going to be that this is going to place a tension force on this joint. And since this is a vertical member, it's likely this is going to be in compression. So 1017 is 2,276 pounds. That's a lot of force. And just to make sure, that is in tension. And then we come over here to 1117, and we're at 1,185 pounds in compression. So there's a lot going on at this joint. We really want to make sure we have engineers prescribe a repair for this, which will basically, they'll take a big old piece of OSB, a big rectangular or square piece, and put it over the joint, lots of nails, and the shear capacity of the nail will resolve these forces that are internal in this joint.